did I do? Oh, I stopped it. Imagine that. Ah, thank you, Mr. Venner. Now, the purpose of your distribution substation is to lower the voltage from your transmission. And we said this earlier. And subtransmission. The subtransmission would be the input you would have gotten from your step-down substation, right? So from your transmission or subtransmission levels to a voltage that can be safely installed on the streets or on adjacent, that are adjacent to the customer's premises. So in other words, your distribution substation will take the voltage from the 69 transmission level down to 24, which is distribution. All right. As I said, I may have said in the past, the distribution voltages in Jamaica, there was a plethora of them, from 24, 2.3, 6.8. It was all over the place. All right, but no, there was a project some years ago which was known as the Voltage Standardization Program, which upgraded all the distribution to 24. Okay, so the purpose of that substation is just to bring it down to the voltage that can be safely used or moved around a particular area. So we now need to delve in some of the key things as it relates to distribution substation. Part of the limitation here is that the right of ways that may be available near to a customer's premises would make that low voltage necessary. And it goes back to what? To the question that Ms. Michael asked earlier, which is a very important question. Very important question that we need to appreciate, as far as power systems is concerned. Because of where an industrial facility ought to be, then you would not be concerned about the types of rights of ways that you'll be dealing with when it comes to a residential area. All right. Now, the towers that would be required for a 69, all right, would take up the land space, just 1 foot of the tower, just one tower in terms of the footing may take up the land space of 2 homes. Now, I doubt you would want to have something like that in your backyard. But those are the facilities that will be required if you were going to be supplying 69 kV. All right. But within a community, within a residential community, what is on the pole is 24 kilovolts, and we are good with that. All right. Of course, you can have your spurs, which are your 415s. Your 3-phase 415s going, down a little lane. You're not going to carry the 24 down that little lane just for, those few houses. Okay. All right. Now, within that distribution substation, you have certain equipment. You're going to have your transformers. Of course, you need to take your voltages down to the distribution level, voltage level. You're going to have your circuit breakers, right? You have relays, all part of your protection, your lightning and surge protectors. You have bus bars, yes? And your bus bars, we have been using it. I mean, we have been talking about nodes in networks. Technically speaking, that's your bus bar. And where we have a source, this is where you start making the links with all that you have been doing. So those voltage sources that you may have seen in a network, in a circuit that we did in networks. Those generators, those sources are really generators. And those generators are connected to a bus bar, which is a node. And those nodes, between those nodes, you have resistance, and you have inductance. Yes? Yes, I throw some capacitance in there too. Yeah. And those may represent the lines that that goes between the generation and the node. All right. So I want you to know, start making sense, because all of those calculations and that question you did in the mid-session, the per-unit question, right? It was just a way of pulling you from networks into electrical power systems and show you that the two really are linked. Okay, so this is where you start now crossing the T's. You have dotted a few I's. We now need to cross the T's and ensure that our learning is for use of a better word, all joined up going forward. So you have your bus bars, you have your disconnect switches. Then you have voltage transformers and current transformers. These are used as part of your protection system. Now, not all these equipment will be used in our substations. All right. So you may not find voltage transformers in our substations, for example. I mean, you will definitely find current transformers, but the types of relays that you will find in substations may not be the same. Some relays you may not need all of them. Yeah. So these things vary. Okay, the type of lightning protection that you'll have in one substation may not necessarily be the lightning protection you'll find in the other. But these are some standard equipment that you'll find in your substation. Now, some of the factors that will dictate the design and layout of your substation, some of those factors are shown. So you have your voltage. Yes. The voltage level would speak to things like clearances. Yes. Yeah. And we'll speak about that in a little more detail in a few minutes. So the design or the layout will be dependent on your voltage, the load requirements in terms of the density and the expected growth. Yes. Also the importance of the load. Now, I tell people that when I used to live in Papine, I was a happy man because I rarely had a power cut. But the power cut wasn't really about me. It was because I live near to the university hospital. All right? Because that's an important load. All right? If you want to never have power cut, then you live near Judges. You have to work this thing out for yourself. But anyway, the other factors, availability of site space. If you are going into places where you don't have enough space, then the layout that you use will have to fit in what is available. The location of the site. And I'll speak a little more to this because only recently there was a court ruling here in Jamaica that spoke not specifically to substations, but to the whole distribution network of an area. Also the protection system sophistication. And we'll talk about protection systems later on, and some general principles around protection. And so the protection system sophistication and cost. Because as I said before, one of the primary objectives of your power system is to supply your customers and to provide them with a reliable supply. And that reliability will be closely linked to the type of protection that is employed. And protection can be from a one wire with your ground to, a multi-billion-dollar system, right? And also, the design of your power system will have to give consideration to other substations with which it will be connected. All right? So, there's an interconnection, for example, between Upper Camp, Hope, and they are the primary substations going into the university hospital. But they, in terms of operation, it is such that if one fails, the other one will continue to supply the hospital. So the hospital will never be out of electricity. But of course, you know, there are other things that are going into place in terms of you know, seeking to provide their own electricity. But they would have to understand that, you know, they still have some dependence on the current utility provider. But the design per se will have to take into consideration the other substations with which it will be interconnected. So let's just delve a little into these, and then we will, that will be it for today. All right. Now, just a couple of notes here. In terms of functionality, all right, this may be the case even within the same company. So you'll have, based on just the functionality of the stations, you will have variations in terms of the design within the same company. So I'll design something for Hope completely differently from how I design it for somewhere in Bath, St. Thomas, or Negril, Westmoreland, right? The considerations may be completely different. Now, standardization would make life beautiful. So if for example, you know, to my own chagrin and disappointment, I know half of you that I'm teaching here today, that in the next 10 years, I'll see you all in North America or the UK. I know that. Well, then again, COVID might change all of that. But that's it. You may end up working for a company that has several industrial facilities and, you know, different substations. And you may find that it will be best that these substations are standardized, because of course it reduces the time that you're going to take to come up with a new design for a new substation should you be opening a new facility. All right. So these are things that I wanted to appreciate. And I may be going into your research methods now. Yeah, I may be going into an area that I have no business going into. But get this clear, students. There is nothing wrong with referencing or looking at what has been done by other individuals, right? In your labs, we call it theory, okay? In research, or for your project, we call it literature review. Good. And when you go out into the working world, you call it reference. So you look at what people have done. There's no need to go and reinvent the wheel. If you go there and you see this is the design that they use for the substation, what you do is to take it, look at it to the extent that it can be used for a new project. You don't necessarily have to start it from scratch. And that is something that you as engineering students need to appreciate. Yep. It's not always about new. It is about looking at what people have done, acknowledging their effort, and then put your own spin on it. Okay? But don't take it and spin it and make it and present it as your own. That's where you get into serious trouble. Anyway, back to standardization. It simplifies construction and maintenance. All right, so your maintenance program can then be simplified. You don't have to have a maintenance program aligned to a specific substation or facility. Whatever that program is, you can roll it out for all facilities if you have standardization. And of course, you know, construction and maintenance. And then of course, stocking of spare parts, that makes life easy. I know of one major facility here in Jamaica, major facility. They are in serious trouble because they're one of their generating facilities, they are struggling to find spare parts, and so they are scrapping one unit to fix up the other. All right, but all right, that's for another time. Okay. We also want to state, however, that overstandardization can result in the selection of substations that do not economically meet the needs of an area to be served. So that is why I said earlier that you look at what has been done. You consider it carefully, but you always then make the adjustments based on what is required for the project that you are looking at. So you make the necessary adjustments. So if the standard thing is that you have two double breaker, double bus, right? It don't mean that when you build a substation to serve that new community that is being built in the hills of Clarendon, that you're going to use double breaker, double bus. You may be able to do a single breaker, single bus down there, and the people will be happy. They don't mind losing power, once a year, right? You don't need to. So you have to consider these things. And remember, as I said, as engineers, your purpose is to save your company money. I'm not saying cutting back on quality of service. That's not what I'm saying. But save money whilst meeting the objectives of the company. All right. Now, one primary consideration is based on the distribution voltage. Remember, we said that voltage, and I had it at the top there. Voltage is one of the key factors in deciding on the layout of your substation. Right? And the highest distribution voltage that can be safely and economically installed in the available right-of-ways. So this one, so what it says? It says safely. Now, I understand that this is a major consideration. I was just talking about you saving your people money. But if it is not done, then we have a problem. Okay? I don't think I need to emphasize that too much. In terms of voltage, you also have the conductor spacings. Now, the conductor spacings will be dictated by the right of way that you have, right? And the right of way the right of way dictate the spacing dictate the voltage levels that you can work with, right? It also speaks to your ground clearance. In other words, the height from ground. Yeah. Now, the size of the load that needs to be served also determines the capacity of the substation. Right. What is the loading? So you're going to buy your transformer based on that. Right? What kind of load are you doing? Remember I said earlier, and you see, I come back to that beautiful question from Ms. Michael. Because the type of load, whether it's commercial, industrial, or residential, yes, will dictate the sort of substation that I build. So if I have an existing substation for a residential community, but the people in that community, everybody are open shop, everybody are open garage, everybody are open salon, everybody, well, I suppose Portmore is a classic case, right? If that continues to happen, it means that the substation would then become inadequate. So zoning is important. We hear now a lot of cries about what is happening on the hillsides. Yes, and it pains my heart to see what is happening. But at the same time, if we as a people don't get into the business of respecting rules in terms of buildings and that sort of thing, and ensure that things are passed and that they're in the right zones, if we don't become strict in those things, you know, we're going to continue having these challenges, and those issues also impact your substation and the facility required to supply power to these customers. All right. Again, the importance of your load, critical loads, just like the hospital, are served with more complex substations. So one of the things we're going to talk about in a few minutes, yeah, we know we're running out of time, but we talk about the bus bar arrangements. All right. Now, some bus bar arrangements provide increased flexibility, but that flexibility comes at a significant cost. All right. So those are things that we would have to give consideration to. All right. So when we do the design in terms of the protection system that is applied, we are saying that it must provide maximum reliability and the speed of power restoration. So even if the hospital loses power, we must be in a place, or we must be able to return that power in as short a time as possible. What are some of the other considerations as it relates to load and voltage and space? Right? We have to bear in mind that we're going to have growth in load, but growth in what type of load? So I suppose when we talk about load growth, persons are going to say, well, you know, yes, they must have had capacity there for increased load. So if a man put up, start run even a tire shop where he's running his compressor, and compressor put on reactive loads on the system because he's now running motors. Right? Now I know that may jar at our own need to do that which provides an income, or provides the wherewithal for our survival. But the fact of the matter is, it has some implications for the operation of the grid. All right? So we have to think about that. But load growth, so we might have excess capacity. Whilst we may not opt to put in the excess capacity up front because, for whatever reason, that may not be the acceptable decision, we may go for having a substation that will be easily expanded. So we can add capacity. Right? Now, the other point is that if we have enough space, then we can play, we can have fun. Right? So if we have a lot of space, we have more design options. We can go to town. Right? However, in densely populated areas, these options can be severely curtailed. And we need to understand and appreciate that. Now, not only are we talking about curtailment in terms of the availability of land, but the land itself can be so expensive that you just have to use what you can afford in putting in that substation. Yes, and then you'll be forced to use a design that requires much less space. The other thing I wanted to mention was, for example, the visual sensitivity of residents. There are some places well, and it happens, I suppose, here in Jamaica that, persons were not too happy to get up and see a windmill every day outside them bedroom window, right? Now, when you're driving along the road down in St. Elizabeth there, and you look up on the hills of Manchester, and you see the windmills, they look quite nice, But I tell you, I kid you not, when you drive by those windmills, they are huge and they can become, well, I mean, I don't know if I can say this about an inanimate object, but they can feel a little intimidating in terms of size. I mean, you're driving beside them and you feel like an ant relative to these things. People don't want that. Same thing with the substation. People don't necessarily want that in their backyard. They don't want to see it. And so it creates or forces you to be involved in more expensive designs, right? Now, I mentioned earlier the issue that played itself out in the courts recently, where persons in Hohe Pastures, they won their court battle against the JPSCO in terms of underground versus overhead distribution lines. And also, even the substations that are in that area are such that if you have to deliberately go and look for those substations for you to see them. So they are partially, I know I'm stretching it a bit when I say this, but they are partially indoor substation, right? And so you are forced to spend more money. So it is the decision of the utility to recoup those money in terms of, when you're going to develop that facility. If that is what going to be the selling point, a key selling point for the individuals who would be living in these areas, then they have to pay that developmental cost up front. Okay, if you're going to put the substation underground just to appease their sensibilities or sensitivities rather, then they have to pay for it. I hope you get the point there. All right. Okay. And now on the downside, we talk quickly about want to talk about substation grounding, and then we look at bus bar arrangements, and then I say goodbye to you for today. Any questions or comments? Or should I say, are you all awake?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
About
There, man, there.
Yeah, I hear a few sounds, so it sounds like enough people are awake.
Sir, but I've heard of that thing that you mentioned in regards to the Hope Pastures. They wanted the system to be underground. This was a United States. I don't remember what state it was to be exact, but the person wanted to live in a particular location. However, there was just high, I think it's a large transmission lines that were there in the area. There wasn't a lot of houses there, and he had to pay for his own generating unit and the utility company in that state would connect it to the transmission grid, I think, transmission lines to get his source of energy from that particular utility company. So he had to stand the cost of paying for that transformer in wanting to live in that particular location.
And I thank you for that. And that is something that happens here in Jamaica, where people just want to live off the beaten path, but they end up being very far from the supply, and they have to just pay the utility company some good money to get the supply to their location. Unfortunately, whilst that may be the case for the utility, when it comes to roads, all we need to do is to just walk through a path long enough, and then soon we'll see a road appear. But that's for another time. We only have half an hour to wrap this up. But thanks
Yes,
for
sir.
that.
Yes, sir.
All right. Substation grounding. Once persons are walking around in a power station or touching, the people have to work there. Let's get that clear. People have to work in there. We don't know when a fault will occur. And when the fault occurs, you can have dangerous voltages occurring between your legs, or when you're touching a piece of equipment. And one of the key ways of reducing this possibility is to have the earthing impedance as low as possible. Ideally, it should be zero, because we know that earth resistance, is supposed to be zero. That's not usually the case. So ideally, the earthing resistance within your substation should be about 1 ohm, right? 1 to 5 ohms, but let me just say 1 ohm, all right? And this is achieved in part by putting in what we refer to as a grounding grid or earthing grid. And all equipment, everything within that substation is connected to the grid. Now, I think I have sent you these photos, so you can have a look at it. All right? So here's a typical substation. And here's your grid. So all of this is your grid, and your grid would be right around the substation. So underneath, so before they put in the substation, they would basically dig out or excavate all of that area, put in the grid. Yes, and then all the connecting points would then come up for your various equipment. So I want you to note that here we have that talk about the switchgear. So that would be your breaker. Note you have a mat. So when you're working on any piece of equipment within the substation, there will be a little mat, metal mat that you need to stand on. And that's for your own protection. Even though you have on safety boots, etc., you would have that. And that is the switch gear. And you saw the little green thing there? That's showing you that it is connected to Earth. Your transformer, connected to Earth. All substations, and some of the things we kind of just pass them, but my purpose here is to increase your sensitivity to a number of things, so you won't just pass them anymore. If you look, all substations are fully fenced, and it's not just to keep you from thieving the equipment, but the fence posts are all connected to the earthing mat. Because although the company has the sign up front that high voltage keep out, right? You're still going to have people maybe hanging on to that fence, holding on to that fence. If you are holding on to that fence during a fault, yes, you shouldn't really have an issue, because all the fence posts will be connected to the earthing grid. All right. Now, a couple of ways that you can reduce the resistance to the grid. All right. Ready? One, in terms of depth. So the deeper you bury it, you can help to reduce the overall resistance. The number of meshes. So each of these, that's a mesh within your grid. All right. So the number of meshes within it. So you can increase the number of copper of meshes. All right, so if you make more meshes, then so that's 2. Thirdly, you have some rods here. You see these rods? All right. Well, they only show 2 here, but obviously there'll be more. If you can increase the number of rods. Right, so you have the number of rods. So those are your vertical rods here. You can increase the number of meshes. So you'd use more wire. All right. You can make this, the grid itself, you can make it deeper. Now, what you'd also note, what they have here is crushed rocks. All right. What those crushed rocks do, they don't necessarily reduce the resistance of the grid. What they do is to increase your step and touch potential. Go again. So the crushed rocks, and if you note, you will not see a whole heap of bush growing in your substation. All right, and it's not only because of the rocks. Remember, they would have taken out the topsoil and put in the grid. So a lot of those shrubbery would have been killed in that stage. But outside of that, you also have the crushed rocks, which increases the step and the touch potential. In other words, it makes the minimum voltage at which you would be in danger. It would make that voltage a little higher. All right. But again, if you want to hear a little more of that, we talk in January. All right. So you can refer to this, your control room. That is where all your relays are located. That again, is connected to your grid. Is there anything else I need to mention here? No, I'll leave that. The next, your bus bar arrangements. So your bus bar arrangements, one, they used to facilitate the number of circuits connected. So the number of circuits, meaning, you can remember we're still talking about a distribution substation here. So the circuits would be the feeders that goes into different communities. So down at Hope, you have 3 feeders. You have one going down, down, what that road name? Anyway, heading towards you. You have one going Hope Pastures Way. You have one going up Papine. Okay? So you have those distribution feeders which go out on the road. And I'm saying the number of circuits will be dictated by your bus bar. So in the sense of your bus bars here, we're not going to be looking at generation, even though generation technically is connected to it, because whatever is the incoming to the bus bar, to the substation, would be, technically speaking, your source. So when you're representing this, when you're doing a study on your substation, what you would establish is a grid point. So that grid point would be seen as your infinite bus. So that would be your input to your substation. All right? But generally speaking, we're talking about the number of distribution circuits when we talk about the number of circuits connected. The bus bar arrangement also speaks to maintenance. And of course, the minimum number of circuits required to be isolated during fault. I'm not going to spend a lot of time on this because that is really for the protection. Yes? And the arrangement that you ultimately use, will be based on the service requirement. What is it that you're really serving? Who are you serving? Yes? And then, is it worth it? What's the cost of providing this service? Yes, so what you use will be based on the service requirement, who you're serving, and 2, what it will cost to provide that service. All right? So that's decision making. And I hope, ladies and gentlemen, and I say these things and I know that sometimes I annoy the life out of you, but I'm saying it, you know. Everything that you're doing, everything that I am saying today is based on the approach you take for your lab. You do your research, you look at the results, you have a discussion, and then you make a decision. So that would be applied to your bus bar arrangement. Okay? Who you're serving? What's the cost? What are the implications? You know, the who you're serving will dictate what's the sort of flexibility that I need. Can these people be without power? If they are without power, for how long? Because that will now dictate the sort of protection that I'm using. Okay? All right. So the first one I want to talk about is a single breaker, single bus. So one bus bar, and to each circuit, you have a single breaker. Right? Very basic arrangement. It works. It is cheap, and it is simple. Right? Use that low voltage, but it doesn't offer much flexibility. The bottom line is, if you have a fault, it trip. You may have a reclose on it, but if you don't, it trip. Somebody have to go check, clear, and reinstall and return to service. So for a single breaker or single bus, single breaker, all right, I'm showing here 4 circuits. So you have these diagrams. Did you get the email? I know I sent it maybe about half an hour before the class. Did you all get the email? Yes, sir. Some of you got it?
So I didn't receive it.
No, sir.
I'm yet to receive it.
All right, I sent it in Schoology, so you can look at it when you have the time. All right. So all these diagrams are already there. So what you'd need to do is to make the notes. The diagrams as shown are there. So here are your circuits. These are your circuits. 1, 2, 3, 4. So I'm providing 4 circuits. Here's the bus. That's your bus bar, and these are your breakers. So what that is saying is that each circuit, yes, so circuit 1 is being supplied from this single bus. So that's a single bus. All right, that's a single bus. And it is being supplied by 1 breaker. So 1 breaker manages that 1 circuit from that 1 bus. All right. I said earlier about VTs, that's something that we would talk about again if you come back in January. All right, so that's your single bus, single breaker. Now you have a single breaker, double bus with what we call a bus tie. All right. So your single breaker, single bus, it's quite similar to your single breaker, single bus arrangement. But it is used where you have at least 2 supply points. Remember what I said before, that the design of your substation will be linked to the design of adjacent stations. So if I have a substation that can get supply from 2 other stations, then I could have my single breaker, single bus with bus tie. I mean, single breaker, double bus with bus tie. Are you with me? So if I lose one, I just put in the bus tie and I'm good. However, that's not really the purpose. The purpose here is that, do we have this?
Yeah.
All right. So with a single breaker, double bus, what is he saying with the bus tie? If I have a fault, then those will open. All right. So if I have a fault over here, all right, then that will open, which means that circuits 1 and 2 will continue to be served. These guys would not be served because these would be open too. But the bus tie opens and allows power over here. You with me? Because bus A would still be supplied by the incoming on that bus. Similarly, it provides greater reliability, because if the supply for B is lost, right? If that supply is lost, I still will have all 4 circuits being served once the bus tie is closed. We understand the increased flexibility? So whereas for this one, if I had a fault on the bus, all of these would open. And therefore, all 4 circuits would lose power. In this case, only 2 of the circuits would lose power if I had a fault on one of the bus. All right? So it is, for example, with a word, this is not totally lost. It is not all lost. But you still suffer some losses. All right? Okay. So we have talked about single breaker, single bus, single breaker, double bus with bus tie. And then just a further expansion, we have a single breaker main bus with transfer bus. Or if you remember all of this afternoon, then it means that, you know, I can give the AI, you just leave it. You know, but so don't feel pressured that all of this information is coming at you. All right. So next we have a single breaker main bus with transfer bus. And if we go back to what I said earlier, in terms of considerations, right? The bus arrangement is used to facilitate 1, the number of circuits, 2, maintenance, and 3, we consider the fault implications. And then, you know, what we use will be based on the service requirements and, of course, cost. So far, in terms of cost, the single breaker with double bus with bus tie, it may cost a little more than the single breaker, single bus, because I have the tie bus breaker included. All right. All right, so the single breaker main bus with transfer bus, quite similar to what we looked at before, right? It's a single bus. The difference here, do we have this? Finish writing? All right, silence I suppose means consent, so we move on. So I have my main bus down here. Under normal conditions, these switches are closed. All right, so those will be closed. And it means that we'd have supply. Let's say if a circuit 1 from my main bus would have it there. For this one, all right? And then for this one. Okay? Now, if, as it says, if we go back to the note, we said that if we need to carry out maintenance, then we can use the transfer bus. So let's go and trace that. For your transfer bus, if you look over here, here's my main bus. Now let us say I'm working on circuit breaker number 4. So this one will be taken out. But we still need to get power to circuit 4. All right? What we will do, we close the tie breaker. Okay? So we'd close that. Now we have energized the transfer bus. Once you have energized the transfer bus, we then close that. So you now get power from the main bus, through the bus tie, through that, and up to 4. So if I take out bus breaker 4, that's how I'll get power to circuit 4. Again, don't stress yourself that you can't trace all that. Today I've given you the circuits, yes, you can go back, look at the conditions that we have laid out here. Yep. And then look at the operation. Okay. Next, single breaker, double bus. So now we're getting into where some important people live in our community, in the community that we are doing the design for. All right. So now we have a double bus, single breaker. What this is saying to us is that we can have supplies through my single single breaker, of course, being supplied from one of two buses. Yes? So one of two buses. Now, the challenge with this is that ready?
Yes, sir.
So here's bus 1. Here's bus 2. My circuits, circuit 1, circuit 2, 3, and 4. All right. Now, if you look on the switches between the two buses, all right, and if you look at the switches between the two buses, that's right here. Let me use red. So between here. All right. If you look on either side, you have normally open, normally closed. Yes? What that is saying, in a nutshell, is that both of them can't be closed simultaneously. That's all it is saying. So you can only get supplied from one bus at a time. So circuit number 4, yes, cannot be supplied from bus 1 and bus 2 at the same time. Can we see that?
Yes, sir.
Right. So in the event I have to take this out for service, I would then go to the normally open side. So I would close that and I would close that. So let me take out all of the ink here. So that would be closed and that would be closed if I have to take this out, right? But then I would close these in terms of providing protection in the event I have a fault on that. Are you with me? So if I get a fault on 4 while I have done the bypass, because the bypass would have been this up here, all right? So that's how I would get power from 4. Under normal circumstances, let me use the blue, I would have done this to 4. But if I have to take out the breaker, yes, I would have gone where you have the normally open. So 4, as it is now, under normal conditions, would have been supplied by bus 2. But in the event I need to supply from bus 1, then I have no problem. So what this is saying is that the reliability has increased. All I have done here, I now have 2 bus bars to supply my loads from. All right. I know I only have 5 minutes and I have 3 more to mention. So for your double breaker, double bus, high flexibility. Don't worry too much about this January argument, but high flexibility, Yes? Very expensive because I'm going to be using 2 breakers for each load. Breakers not cheap. All right. So in terms of the diagram for this one, yes. Here's circuit 1, circuit 2, circuit 3, circuit 4. Here is bus 2, here is bus 1. Okay? What we're saying is that circuit 1, 2, and all the circuits are supplied by 2 breakers. So you have a breaker on this side, you have a breaker on that side, which service, in this instance, circuit 4. This one supplies circuit 3. That for circuit 2. So in the event I have a fault on this bus bar, all right? And based on your lab, you know that the more severe fault occurs the closer you get to the bus bar, or not, no, let me rephrase that. Your more severe fault occurs on the bus bar. All right? As you go away from the bus bar, the severity of the fault decreases. So you have that fault on the bus bar, it means that all of these would trip. But although they trip, the customers 1, 2 to 4, or the customers on feeders 1, 2 to 4, would not even know that they have had a fault. Because although all these breakers have tripped, yes, all these breakers would remain in service. So that the customers wouldn't even know what was happening. But as I said before, expensive, and you would have to determine whether or not these customers are important enough for that consideration. All right, ring bus, high flexibility relative to the number of breakers. If you take one out, if you take out a breaker, nobody would know. Yes. But we have some other protection issues. Again, don't worry too much about that. January argument. All right. But we can take out a breaker and the supply is maintained. All right. So the question is, I mean, with this great level of flexibility, are we using four breakers, which is similar to the single breaker, single bus? Why then not use this? That is it. That's part of the reason. So whilst it does the job and does it beautifully, because if I take this, if I take out any breaker, and I know we are at 1 minute to 5. If you must leave, I understand, right? If we take out any breaker, let us say I take out this breaker, all right? You realize that I am still being supplied. All 4 loads will still be supplied, right? Because I take that out, everything else is connected. So all 4 loads will be supplied just the same. Right? The only problem is I can't apply differential protection to this, which is a major problem. All right. And then lastly, we talk about a breaker and a half. And the term breaker and a half really means that you have 3 breakers used to supply 2 circuits. All right? So if you have 3 breakers supplying 2 circuits, yes, then we technically say you have 2.5 breakers, 1.5 breakers to each circuit. Of course, you can't have a half breaker. Right? So it's 3 breakers to 2 circuits. That's how we need to look at it. and it is very flexible. Note that it is in the mid-range between double breaker, double bus, and single breaker, single bus. All right, so it's in the middle there, between two, and yeah. So in terms of your figure, this is what it looks like. That's a breaker and a half. So you have two circuits. So you have one circuit here, you have one. And then these are the three breakers. You have bus A up here, you have bus B down there. Yep. And those three breakers would supply the units. So if I needed to supply these two while this is out, or if I have a fault on this, if I have a fault on this, then if I have a fault on bus B, these two breakers will be out. So they'll separate that bus bar, but the four circuits, all right, would still be served by these four. All right, folks. I know that's a mouthful today. Yeah. But just whilst we absorb all of that mouthful, I still need you to just respond to your names while as we wrap up today.
So, sir, just a question before we move on. So, essentially, the principle behind using breakers in circuit is to use the minimum amount that can provide like maximum functionality of a circuit or grid that you're operating on.
That's the best summary I've heard in a long while.
Okay.
That's exactly what we want to do. We want to provide maximum reliability, maximum efficiency, lowest possible cost. All right? All right, Mr. Adams.
Present.
Allen,
Yes, sir.
Barrett, Spirit. Barrett not with us. Let me just make sure. Okay. Okay, Blake, Raji.
Yes, sir.
Here, sir.
Bruce. Bruce. Buckley. Lewis. Buckley. Burns.
Yes, sir.